Hello everyone, this is Jesse Crawford with Tarleton State University, and we are ready for our next video in the Foundations of Mathematics course, which is going to cover partitions. This first slide here gives us the definition of a partition. It says, let A be a set. A partition of A is a set of non-empty pairwise disjoint sets whose union is A. Let's jump into some examples. So the first thing to point out here, we have a set A, which is a set of integers from 1 to 6. And we're trying to determine if the collection that's listed underneath A is a partition. So the first thing you'll notice right away about this set that's written here is it is a set whose elements are sets. This is often called a collection. So it's pretty common when you have a set that contains other sets to call that a collection. So that's a first very important point, is that by definition, a partition is a set of sets. So it's always going to be a collection of sets. Now, what properties do those sets have to satisfy for this to be considered a partition? They have to be non-empty, they have to be pairwise disjoint, and the union of all of the sets has to be the whole space A. That's what we need. So we just go through and we need to check all those conditions. Are all three of these sets in this collection non-empty? Yes, they are. Are they pairwise disjoint? Yes, because the first two sets don't intersect, the first and third sets don't intersect, and the last two sets don't intersect. And is the union of all of the elements in this collection equal to the whole set A? And the answer is yes, that is true. So this first example here is a partition. Let's look at another example. Is this a partition? Well, these are non-empty sets, and the union of these sets is the whole space A, but they're not pairwise disjoint, right? They overlap, so this would not be a partition. What about this example? These are non-empty sets. They are pairwise disjoint, but their union isn't the whole space because the number 6 is not listed in any of these sets, so this is also not a partition. What about this guy? Here we've got some sets that are pairwise disjoint, and their union is the whole space, but one of them is the empty set, and that's not allowed. So when you're dealing with a partition, every element inside of it is required to be non-empty. And then we can look at this example. This might look kind of weird, but this technically is a partition. It is a collection that only has one set in it. The one set that's inside of it is non-empty. The union of that one set does give us the whole space. And in almost a vacuous sense, that one set is pairwise disjoint, because pairwise disjoint says that if I take two different sets, that their intersection will be empty. But if I only have one set to start with, I can't even take two different sets, right? So in sort of a vacuous sense, these are pairwise disjoint. So this actually is a partition. And also this last example is a partition. We have a collection of sets where every set in here is non-empty, they're pairwise disjoint, and their union is the whole space. So why are we interested in partitions? Well, all of the language that was given in this definition is probably sounding a little bit familiar. Non-empty pairwise disjoint sets whose union is A. Let's actually scroll back a bit. We might be able to see that this appeared recently. Yeah, it appeared down here, right? It says if R is an equivalence relation, the equivalence classes are non-empty pairwise disjoints subsets of A whose union is equal to A. So in other words, an equivalence relation always produces a partition for us. And in fact, that's what this little statement at the bottom of this page says. If we let R be an equivalence relation on a set A, the equivalence classes form a partition. And again, we don't even need to prove this because we've already proved that. We proved that in our last lecture, right? And that was the proposition we just scrolled back in the slides and looked at. It might be nice to look at an example of this. So one of the relations that we looked at in our last lecture was congruency mod 3. And we talked about, for congruency mod 3, that there are basically three equivalence classes, bracket 0, bracket 1, and bracket 2. And you'll notice that these equivalence classes are all non-empty, and they are pairwise disjoint. They don't overlap at all. They don't share any elements. And if you take the union of all of these classes, you will get the entire set of integers. Every single integer is somewhere in one of these. And so that means these three sets constitute a partition. Now again, a partition is a set whose elements are sets. So the way that you would write that in this case is you would say the partition P is a set containing bracket 0, bracket 1, and bracket 2. So yeah, this proposition tells us that anytime we have an equivalence relation, the equivalence classes of that relation give us a partition. So another way to say that would be that every equivalence relation produces a partition for us. So another interesting question might be to ask, is it possible that we can take a partition and get that to produce an equivalence relation for us? So we can go in this direction. Is it possible for us to go in the other direction? It is indeed possible for us to do that. Okay, this is how this is going to work. We're going to assume that we have a set A and we have a partition on that set A. So again, we're trying to see if we have a partition, can we create an equivalence relation? That's the goal right now, right? So we're going to look at, let's look at a set A, and let's let P be a partition on A, and let's see if we can define an equivalence relation on that set. And here's our definition. We're going to say that A is equivalent to B if and only if there exists some set P inside of the partition script P such that A is in P and B is in P. This definition is a little confusing, and so why don't we look at some examples to try to get a handle on what this is saying. So earlier we were talking about the set A, which is all of these integers from 1 to 6, and one of the examples we saw of a partition was this one, right, where we have 3 sets, 1, 2, singleton 3, and 4, 5, 6. So let's just go through and see if we can make sense of this relation here. So one question we might ask is 1 related to 2? So this definition is telling us that 1 is related to 2 if we can find a P in the partition where A is in P and B is in P. So this P is one of the sets that's inside of the partition. So if we can find one of the sets in the partition where 1 and 2 are both in there, then 1 is related to 2. And of course, that set exists, right? It's this set. So the answer to this question is yes, 1 is related to 2 because the set 1, 2 is an element of the partition, 1 is in that set, and 2 is in that set. So this is how this definition works. So basically, to make sense of this, what this really says is 2 elements are related if and only if they're inside of the same partition element. So like 1 and 2 are inside of the same partition element. Another example would be 6 and 4. Well, yeah, 6 and 4 are inside of the same partition element, so they are related. And we can write that out, right? So we can say, yes, 4, 5, 6 is inside of the partition element, and 6 is in this set, and 4 is in this set. Now you'll notice it sometimes gets tedious to write out 1 is in here and 2 is in here. So instead of doing that, we can just write 6, 4 is in here. This doesn't mean like an ordered pair or anything. I'm just saying the element 6 is in here and the element 4 is in there. That'll be kind of nice for brevity's sake. What about 2? Is 2 related to 5? And no, it's not, because there's not a partition element that contains 2 and 5. So the way that we would respond to this is we would say, no, there does not exist an element P inside of the partition script P such that 2 and 5 are both in that element P. So no, 2 and 5 are not related in this situation. Poor little 3 is all by itself here. We might want to ask, is 3 related to anything? Well, it is, because 3 is related to itself. 3 is related to 3 because the set singleton 3 is inside of this partition. 3 is in that set, and 3 is in that set. It might feel kind of silly to say that twice, but technically that's what this definition requires. And so it is true that 3 is related to 3 because it does satisfy this definition. And you can play that same game with anything. Like you can ask, is 4 related to 4? Yes, because the set 4, 5, 6 is an element of our partition. The number 4 is in that set, and the number 4 is in that set, and therefore 4 is related to itself. And it's not too hard to see that that process is going to work for every element of the set, and so every element is related to itself. As a result of that, this type of relation is always going to be reflexive. And so that actually starts to lead to the next part of this discussion, which is our goal earlier was to see if whenever we have a partition, does that actually define an equivalence relation? That's the goal that we're trying to investigate right now. And what we've basically done so far is we've said if we have a partition, we've defined a relation, but is it actually an equivalence relation? It's not just automatically true that every relation is an equivalence relation. You have to show that it's reflexive, symmetric, and transitive, right? Those are the three properties that we discussed in detail in our last lecture. So that's what we need to do now. And we basically gave a pretty good argument here that it looks like this relation is reflexive, but we need to investigate symmetric and transitive. All right, so that's actually what this slide talks about. It says let A be a set and P be a partition, and we're still defining A is equivalent to B in the same way. We are going to now prove that this relation is indeed an equivalence relation. So let's go ahead and do that. So I'm going to go ahead and tab over to this document, which has that information in it. So before we get into this and we start actually trying to prove that this relation is an equivalence relation, let's remind ourselves what all the properties of a partition are so that we can take advantage of these. So we know four things that result from the fact that P is a partition. First of all, this first bullet point is just a reminder that every element of a partition is non-empty. So for every P in script P, P is non-empty. The second statement is a reminder that the elements of a partition are pairwise disjoint. So for every P1 and P2 in a script P, we know that if those are two different sets, they have to have an empty intersection. So if we take two different elements, that's kind of what this is saying, right? If we take two different elements of a partition, their intersection has to be empty because those elements are all pairwise disjoint. Now, in our last lecture, we used a trick where it turned out that it was really helpful for us to do the contrapositive of this. Instead of saying P1 is not equal to P2 implies that P1 intersect P2 is empty, we take the contrapositive of that and we say that P1 intersect P2 is not empty implies that P1 is equal to P2. So if you take two partition elements and they have anything in common whatsoever, they have to actually be the same partition element. That's what this is telling us. And then the last property that we just discussed earlier about partitions is that the union of all of the elements of a partition must give you your entire space A. So these are all the properties that we have for partition, and our goal right now is to prove that the relation that we just see with respect to P is indeed an equivalence relation. So as we know, we have to check three things. We have to check, first of all, that this is reflexive, and then we'll check that it's symmetric and transitive. So let's go through that. So to show that this is reflexive, we have to show that for every x in the set A, that x is related to itself. So to handle this universal quantifier, we're going to go ahead and let x be an arbitrary element of A. And right away, we can take into account that the union of all of these partition elements is A. And so if x is in A, x is in this union. So we know this. We know that x is in this union. But if x is in this union, it's got to be in one of these sets, right? So x has to be in P for some P in this partition just by the definition of union. Now, if x is in P, another way that we could write this is, and again, this might look kind of silly, but we can say there exists a P in script P such that x is in P and x is in P. Like no one can stop us from writing that twice. And what we've really written here is we've written the definition of the relation that we have here, but instead of having it A related to B, the way we've written it here is we've written it such a way that x is related to x. So this line right here is telling us that x is related to x by definition of this relation. And so we're done with this first part. So we have now shown that for every x in A, x is related to itself, and therefore this is a reflexive relation. Let's move on to symmetric. This one's a real quick proof. So to show that something's symmetric, you need to show that for any two elements, x and y in your space, that if x is related to y, then y is related to x. So we'll go ahead and let x and y be arbitrary elements and assume that x is related to y. Well, then by definition of the relation, that means there exists some P in our partition such that x is in P and y is in P. That's just the definition of our relation that we just had up in the slides. But the AND operation in Boolean logic is commutative. If something and something is true, well, then when you reverse it, it's still true, right? So this statement is still true when we reverse the order of this AND operation. But now that we've reversed this, this is literally just the definition of y being related to x by this relation. And so that's it. So that actually proves this relation is symmetric. Let's keep on going here. We also want to show that this relation is transitive. Transitive, of course, is saying that for every x, y, and z in the space A, that if x is related to y and y is related to z, that implies that x is related to z. So we'll let x, y, and z be arbitrary elements of A and assume those first two relations hold, x and y and z. Now, if x is related to y, that means there's a partition element P1 such that x and y are both in that partition element. Again, just the definition of the relation. And if y is related to z, there is also a partition element. But the thing is, it might be a different one. In theory, hypothetically, it's possible that this partition element might be different. So we're going to give it a new name. We're going to call the first one P1 and the second one P2. So there is a P2 in the partition such that y and z are in P2 by definition of this relation. But we're actually going to prove very quickly that P1 actually has to be equal to P2. And the reason for that is you'll notice that y is in P1 and y is also in P2. Well, that means y is in the intersection of P1 and P2, just by definition of intersection. But we set up here that if the intersection of two of these partition elements is non-empty, that implies they have to be the same partition element. And so that's actually happening here, right? Y is inside of P1 intersect P2. That means the intersection of P1 and P2 is non-empty. But that means P1 equals P2 because we just said, essentially this boils down to the fact that the elements of the partition are pairwise disjoint. And we're kind of looking at the contrapositive of that, but the contrapositive of that is equivalent to the actual statement. So we know that P1 is equal to P2. Now, why do we care about that? Well, the reason that's interesting for us is Z is in P2, but P2 is P1. So that actually means Z is in P1, and also X is in P1. So what we can say now is that there exists a P1 in script P, such that X is in P1 and Z is in P1, but that means that X is related to Z by this relation. That's the definition. And so we are done now. We have shown that this relation is transitive. And so the overall conclusion, this relation is reflexive, symmetric, and transitive, and therefore this is an equivalence relation. Okay, well, let's get back to our slides and see what else we can say about this relation. So not only is this an equivalence relation, but we can say something even a little more detailed than that. We can also say that the equivalence classes of this relation are the elements of P. So it might take a bit to sort of think about what this is really saying. So we have some set A, and we have a partition P on that set A. So again, a partition P divides this set A into a bunch of subsets. And what we've just shown is that we can create a relation here. Now, what this last bullet point is saying is that if you take that relation and you look at its equivalence classes, that gives you precisely the same elements that are inside of your partition. And so this is the next thing we're going to prove. So let's go back and take a look at that. So the equivalence classes of this relation are the elements of the partition. Okay, let's take a look at this. So this is actually a really good example of a mathematical situation where we can prove a lemma first. Now the idea of a lemma, this is something that we talked about way back in chapter 1. A lemma is just a theorem, but it is a theorem that you are very specifically proving for the purpose of proving another theorem for later. So you can think of a lemma as almost like a machine or a tool that you are building so that you can complete another task in the future. So a lemma is kind of like a workhorse that you build that you then use to do another task afterwards. So the lemma so we want to prove the result in the slides here. We want to prove that the equivalence classes of the relation are the elements of P. But this is a little bit hard to prove directly. However, if we prove this lemma first, it ends up being super easy to prove that statement. So let's go ahead and jump into that. So the lemma that we want to prove is that if x is inside of p and p is inside of script p, then it turns out p has to be bracket x, where bracket x is the equivalence class of x with respect to this relation. So let's prove this. Keep in mind that P is a set because it's an element of a partition, and bracket X is a set because it's an equivalence class. So if we want to prove P is equal to bracket X, we need to do the standard thing of showing that P is a subset of bracket X and showing that bracket X is a subset of P. So let's go ahead and just let Y be an arbitrary element of P. Now, that means since Y is in P, well, that means there does exist a P in the partition such that Y is in P. And but the thing is, X is in P also because we've already assumed that up here. So you'll notice that this is again just exactly the definition of Y being related to X. So Y is related to X by definition of the relation. But if Y is related to X, Y is in bracket X, right? That's what the equivalence class of X is. And so we've taken an arbitrary element of P, we've shown that it's in bracket X, and that shows that P is a subset of bracket X, right? Let's go the other way. So let's let Y be an arbitrary element of bracket X. Well, if Y is in bracket X, Y is related to X. And if Y is related to X, there's got to be a partition element that Y is inside of and that X is inside of. Now, again, a priori, we can't just assume that that partition element is the P that we started with up here. You know, hypothetically, it could be a different one. So what I'm saying here is I'm saying there exists a P tilde in script P such that Y is in P tilde and X is in P tilde. Now, if you're thinking, is that tilde like a mathematical operator that's acting on P or something? No, that is not what's going on. Like, basically, this will happen a lot. You'll be reading proofs and you'll see this pretty frequently that you'll have one variable, like here I have the variable P, and then you'll have another variable called P tilde, and that's just a totally different variable. But the reason you're writing it as P tilde is to sort of indicate that it's the same type of object as P. So P is a partition element, and so when you see P tilde, it's sort of saying, that is another partition element that, again, hypothetically could be a different one, but we're about to see very soon that they're actually the same. So yeah, it turns out they're the same for exactly the same reason we saw earlier. We have this P tilde where Y is in P tilde and X is in P tilde. But we've already assumed way up here that X is in P. So if X is in P tilde and X is in P, that means P intersect P tilde is non-empty. But yeah, again, like we saw in the previous slide, that means P has to be equal to P tilde because these are pairwise disjoint elements. But if P is equal to P tilde and Y is in P tilde, that means Y is in P. And so we're done with this lemma now. So we have taken an arbitrary element of P and showed that it's in bracket X. That shows P is a subset of bracket X. We then took an arbitrary element of X and showed it's in P, and that proves that bracket X is a subset of P. And therefore, we have shown that P is equal to bracket X. And that's what this lemma was trying to do. So we're done with this lemma. That, you know, lemmas have this property pretty frequently. You look at them, you're reading them, and you're just thinking, man, what is the purpose of this? This seems just kind of like a weird statement, and it kind of feels like it's coming out of left field. But now that we have this lemma in our arsenal, when we come down here, we're going to prove our proposition now, and this lemma is going to make it super easy to prove this proposition. So this is the proposition we just had in the slides. What that proposition in the slide says was that the equivalence classes of this relation are actually just the same thing as the elements of the partition. Now, this really means two things. On the one hand, this means that every equivalence class of our relation is an element of the partition, so we need to show that. But this also suggests that every element of the partition is an equivalence class, so we need to actually do both of these. So let's just go ahead and jump into this. So let's prove this statement first. We'll go ahead and just let C be an arbitrary equivalence class of the relation. Well, if it's an equivalence class, it has to be equal to bracket X for some X in our space A. That's just by definition of equivalence class. Now, we know that X is related to X by this relation because this relation is reflexive. We've already proven this is a equivalence relation. So X is equivalent to X. But again, that means by definition that there exists a P in script P such that X is in P and X is in P. There's this kind of silly thing we're doing again where we're writing this two times. But now, hold on a second. This says X is in P, and it says P is in script P. But that's what our lemma was talking about, right? X is in P and P is in script P. And what does this lemma say? It says whenever this happens, P equals bracket X. So now that means we can just write that down. That means that P is equal to bracket X. We can just write this here. P is equal to bracket X. But bracket X is C, and that means C is equal to P. Now, why do we care about that? Because keep in mind what our goal is on this proof. We're trying to show that every equivalence class of the relation is an element of the partition. We let C be an arbitrary equivalence class, and we showed that that equivalence class was equal to the partition element P. So that shows that every equivalence class of this relation is a partition element. So yeah, we knocked this out really quick. Let's go ahead and do the other direction now. So now we'll go the other way. We need to show that every element of the partition is an equivalence class. So let's go ahead and let P be an element of the partition. Well, one property a partition has is everything inside of it is a non-empty set, right? So we know that as soon as P is in this partition, it has to be a non-empty set. Well, that means there's something in there. That means X is in there for some element X. But now we're done again. X is in P is in script P, and our lemma up here says that if X is in P and P is in script P, then P is equal to bracket X. And so we're done. We just know now that P is equal to bracket X. And so what does that show? That shows an arbitrary partition element P is equal to an equivalence class bracket X. That shows every element of the partition is an equivalence class. So this is a really great example of lemmas in mathematics. Usually a lemma, it's this kind of weird statement. It's kind of maybe hard to think about what it's doing, and you're sort of not sure what you're up to. And then you prove this lemma and you go down, and this theorem is just really efficient, right? Because what we would have to do if we didn't prove this lemma first, we would have to go down and we would have to go through that entire argument here, and then we'd have to go through the entire same argument again. And that's just really inefficient. It's not elegant. It's kind of confusing for your reader, and it's hard to follow. So that is really a good example of using lemmas in math. Okay, well, if we go back to our slides here, we have now demonstrated this. So not only have we demonstrated that this relation is an equivalence relation, but we've demonstrated that its equivalence classes are actually the exact same things as the elements of our partition. And so we've really resolved this question. The first thing we did in this discussion is we defined what a partition is. A partition is a set of non-empty pairwise disjoint subsets of a space whose union is equal to the entire space. So that's the first thing we looked at today. We defined what a partition is. And then we just kind of reminded ourselves from our last discussion that an equivalence relation always gives you a set of non-empty pairwise disjoint sets whose union is the whole space, because the equivalence classes of an equivalence relation have that property. So the first thing we saw today is that every equivalence relation produces a partition because the equivalence classes are a partition. And then our question was, would it be possible to take a partition and produce an equivalence relation? And we have now demonstrated that, because what we've shown is that if we have any set A and any partition on that set A, that this definition here is obviously a relation, but what we've proven is that it is an equivalence relation. So this other direction has now been demonstrated. And it's kind of, again, like almost a deeper result, because there's this additional structure that the equivalence classes of this relation are precisely the elements that gave us the partition. So yeah, that was kind of a quick discussion for today, guys. But again, these are our homework problems. And as always, just let me know if you have any questions. Just feel free to email me. Feel free to post some questions in Canvas, and I'll be happy to get back to you. So hope you all have a great day.